Because I kept messing up. When's that green lab from last Friday due?
Last week sometime.
All right, so like I was trying to say before my computer decided to be a monkey, if you entered this data into your calculator, the way the video walked you through, you would have found that when you did concentration versus time, that you ended up with a graph that looked like this. That is not a straight line, okay? So this is not a zero order reaction. Then you were supposed to do the natural log of that concentration versus time, and you would have found that that is a straight line. There is a further step to do where you can do 1 over concentration versus time. If that's a straight line, then it would be the second order. Since this one ended up being a first order, don't waste your time going on and doing the next step. Now, if this ended up being wrong, you want to do the next step because you want to verify that that comes out as a straight line. Because if none of them come out as a straight line, you probably screwed something up. Because in AP Chem, it has to be either 0, 1, or 2. Okay? So verify it until you get a straight line and then walk away. That makes sense? Okay. So this one you should have found was a first order reaction. Okay? And then they want you to calculate K. All right? The slope of the line is going to be K. So you should be able to determine that. You should have been able to get 3.15 times 10 to the negative 3. It's first order. So your units are going to be 1 over 1 over, and then look at your time unit, minutes. Okay. All right. Then you were supposed to do the we do here. You had a video to watch for that. They told us on here, we're trying to figure out what reaction this is, and we've just been given data. So again, you can plot this into your calculator. The other thing that you could notice is that every 30 seconds, this goes down by half. And since that's a constant amount, that makes this a first order reaction because it gives you a half-life. Okay, so that's the other thing that you could notice, and that would take you a lot less time than going through and plunking all of this stuff into your calculator. Okay, you could also figure out what K is. So K would be your
Happy Tuesday, Loki.
okay. So this only works for first order reactions, right? But you could calculate, they didn't ask you to calculate K, but we could, okay? Because you know your time here is 30 seconds. So 30 equals 0.693 over K. And then you can just solve for K. Make sense? So that's another way that you can do that. Now, were there any questions on the homework from this section?
Number 3.
Number 3? Okay, number 3 says that we have 93.75%. It's remaining after 24 hours, and they want to know the half-life. Okay, so all right, so we know that how do we know that this is a first order reaction? So somehow they would have had to identify here, and I think that there's an issue maybe with this question. They needed to identify that this is a first order reaction. The other thing could be that they're just assuming that since it's talking about half-life, you have to know that it's a first order reaction because we're only doing half-life problems with first order reactions, but they would have to give you that much at least. Okay. So we had talked about some of these equations the other day. We had this chart here where we had first order reactions. We were given this equation. Remember that guy from last week? Okay. So that's what I'm going to use for this. So I've got my natural log this is driving me crazy. Natural log of 0.9375 because I'm trying to record it. And I think I'm going to send this to IT and let them see what's happening because I don't know how to fix it. And it's making me crazy. It's making me absolutely crazy. Let's see if I can plug this guy in and if he will let me write on him. Yes. Okay. All right. Oh, and that happens. Okay. Here we go. All right. So we are over here. There we go. So 7.5. And then we are going to minus our initial amount, the natural log of our initial amount, which would have been 1. Right? Because we started out, this is how much remains percent wise. This is not this problem up here, by the way. So this is number 3. Okay. So then that is 1. That is going to equal our negative K. And over this time period, according to this problem, this took how long? 24 hours. So we're going to multiply that by the 24. Okay. Go through, solve for this guy. We're going to end up getting K equaling 0.0027. That's 1 over hours because it's a first order reaction. Okay. Then you can take this, you can solve for T1/2. That's going to equal 0.693 over our K value, which we just calculated, 0.0027. So our time, our half-life, will end up being 258 hours. What was that? Yep, because they're talking about half-life, okay? So if they're talking about half-life in AP Chem, that has to be a first-order reaction. Yep.
So for number 5, it's kind of like the same thing.
Yep.
How do you know that's supposed to be first order? Because it doesn't mention it.
Good question. Looks like I might need to update these questions a little bit. So number 5 and number 3 need to be told that they're first order. Is that right?
Yes.
Okay. What about any of the other numbers on there? Okay. Okay, I got a note to myself. It'll be better for next year, maybe. But sorry you guys had to sacrifice. Okay, do you need me to run through that problem even if you know that it's first order then?
No, I just pages missing an answer sheet in 5.2 as well.
Okay, let me just write that down for me somewhere. I'll deal with that later. Okay, everything else? Yep.
How do we know when to use that equation in the natural log? And
So if you're given concentrations such as you're given, they gave you a K value, they gave you an initial amount, and they gave you a time. Okay. So if you're given all of that stuff, then that's going to be a time where you're going to use that equation. Because you have all of the variables for it. You just kind of have to look at which equation you have the variables for. And whichever one you have it for and you can solve it the fastest, go with that one. Okay.
Where did you get the 18 for the minus ln 18?
This?
Yeah,
That's not 18, that's 1.
that's 1.
Because it'd be 100%. It's just a very sad looking one because I was trying to do it with this thing and I can't even figure out where my cursor is on this thing right now. It's over there. Okay. So then, yeah, this was a 1 here. So this was 1.0 in there. Now I'm trying to write on this thing and it's not level or steady. So 1.0 was what was in that bracket. Sorry if it looked like an 18. And this was number 3 on your I do, you do, we do. Okay. Ready to move on to 5.4? All right. So, you know how when you've gotten an equation in the past, you've just seen that equation, it's just there. So for example, if you had an equation that looked like this, and we would have to get that guy balanced. Needs a 2 over here. All right. So this equation shows you what you started with and what you ended with. There's actually usually a couple reactions that go on, and then they just get combined to look like this. Okay. Kind of like your redox reactions where you had the reduction and the oxidation, and then you combine them into one reaction. Or, if you want to try to think about like a trip to, say, Florida, okay? you would be saying, I'm going from Wisconsin to Florida. But in reality, you're going from Wisconsin to O'Hare, and then you're going to Florida, right? So there was 2 steps there in that process. And that's what we're going to be talking about today, are these elementary reactions, where we've got these 2 or 3 sometimes steps that go in to make an overall reaction. Think about like photosynthesis, for example. Okay. Do you remember photosynthesis from biology? They give you one equation for that, right? They give you the carbon dioxide and they give you the water, and then you come out with glucose and oxygen, right? But if you remember correctly, it wasn't just going from there to there. They went through all of these different cycles and all this, production of ATP, and there was a lot of different reactions that were actually going on there that, behind the scenes were happening, whereas you just saw the one equation. So that kind of gives you a little bit of background for what we're talking about today. We're not going to do anything as complicated as photosynthesis or cellular respiration. Everybody go, whew. Yep, we'll save that for bio. Okay, so it's unlikely when you look at this equation, okay? In order for this reaction to occur, you would need to take, where's my thing? 2 of these and 1 of these, so 3 things, and get them to collide together to produce this in the right orientation. All right. So the chances of that happening are usually pretty slim. So typically we end up with a reaction where we have this guy forming into this, and then that guy going on to collide with your oxygen and forming this as a final item. Okay. Now, these things in here that form and are reused up before we get to the end, those are called intermediates. And we end up canceling those out when we're giving the final balanced equation. Make sense? So go to O'Hare, go to Florida. 2 steps. But we just say Wisconsin, Florida. Make sense? And then we cut out O'Hare. We don't tell anybody about O'Hare. We just say, yeah, I came from Wisconsin. Done. Boom. Okay? So these things are called intermediates. So you need to be able to kind of see those in your mind and cross them off. All right. The molecularity of the reaction describes how many molecules have to collide in that elementary step. Okay. Both elementary steps are bimolecular, meaning that they have two things that are colliding. Unimolecular reactions then are only going to involve one particle, and they might be some sort of decomposition, nuclear decay, or isomerization, which is just a fancy word for saying that we're going to take the same stuff, we're just rearranging the shape of it. Okay. So there's like glucose, for example, C6H12O6. There's several things that have that same formula, and they're not glucose. It's just the way those molecules are arranged. Okay. So termomolecular reactions are going to involve 3 things. They typically are pretty rare because to get 3 things lined up in the correct orientation is very hard. Okay. So they're talking about here, if you've attempted a 3-person high five, okay, a high five between 2 people is possible. 3 people, it gets very difficult. Okay. And if you're doing like a whole team, good luck. Okay. So the rate law then can be defined from the elementary step based on the number of molecules that have to collide. So for example, here, our rate law for this guy would be K, NO, and then 2. This would end up being a second order reaction. The rate law for second order reaction, or the second one, would be N2O, and then O, these are first order each, because there's no coefficients with them. So this would also be a second order, because 1 plus 1 gives you 2. So you can get the rate law from that equation. All right. Sometimes you are given information about the speed of these elementary step reactions. The slowest step is known as the rate determining step. So imagine that you're working at a chocolate shop, okay? And at that chocolate shop, it takes you 15 minutes to make the chocolate, 8 hours for it to cool, and 5 minutes to box up. What's limiting you from putting those out on the shelf? The cooling time, right? So that's going to be your slow step. So the slow step of the reaction is going to determine the rate of the reaction. The first step is slow, then the overall rate then would be based on that reaction. Okay, so our rate would equal K, and then we would have A2, because there's 2 of these. This would be a second order reaction. Good? Okay. So if subsequent elementary reactions are slow, then you have to add up all the reactants to the slow step and cancel out intermediates to determine the reaction rate. Okay? So here, for example, this is my slow. Okay? So I have to add this up. So I know that this is my slow step. I have to go backwards then. So where did B come from? Well, B came from 2 A's. So we're going to get rid of B, and this is going to be A plus C. So that's where they get this rate law here. You've got 2 A's now and a C that go into that. It's kind of like substitution in math. It's kind of the same idea. Where did B come from? B came from this reaction up here. And what made that up were these 2 A's. All right, given the elementary steps here, what is the overall reaction? And then what is the rate law for the elementary step 1? So they're telling us that they want the rate law for this guy. So overall reaction, we're going to look for those intermediates and we're going to cross them out. So this guy and this guy are in the same amount. It's the same stuff. This was a product. It's getting consumed down here. So it's going to go away. So I cross those out and I write down my rate law. Or not my rate law, I'm sorry, my overall equation. So I write down everything that remains on my reactant side and everything that remains on my product side. And that is my overall reaction. Then they want to know the rate law for elementary step 1. So they're telling us that this was our slow step. So that's going to be rate equals K. And then I've got 2 HIs here. So I'm going to do my HI. And then I'm going to square that. Yep.
So when it says elementary step 1, that means that the first step is the slower one?
Yep. Yep. They're telling you here that if they want the rate law for that, that is the rate determining step. Good. All right. So we've got cyclobutane here, C4H8. It is going to decay into 2 C2H2 molecules. Write a balanced equation for the reaction. Then write the rate law based on the stoichiometry of that elementary step. So I did this as I was talking through it because it says that there's going to be 2 of these. Our rate then,
Wouldn't it be H4?
yeah, it'd be H4. Sorry. Better? That's a 4, you guys. 4. Not a lightning bolt. I know it looks like a lightning bolt. It's not a lightning bolt. It's a 4. Okay.
So the only purpose, like, what's in the brackets, like the reactants?
Yep, just the reactants. Yeah, there's no coefficient here, so that's why there's no number out here. If this was a 2 or something, then we would have to have a number out here. But there's only one of those, and it says it's unimolecular, so it verifies that there's only one of them.
So is what goes into the like K and rate and everything always gonna be the first like thing in the reaction?
The reactants? Yeah, for whatever rate determining step you are, whatever the rate determining step is. Yay. Okay, that's it for today. So work on your lab. I'm going to work on trying to figure out how I'm going to do my next set of lessons.